Okay, this is the tricky second part, right? There's always a 4 and a 5, and they're always exactly the same. I want you to find everything about it. Its position, its velocity as both a component vector and a angle magnitude vector. If you can do that, you basically own the problem. So that's what we're going to do here. So let's fill this in. We are going from, let's draw a little picture here. Here's this cliff. Right, it ends up going 12.4 out, but we're just talking about some arbitrary horizontal distance, right? This ball is going, and we want to know it right there. How far over, how far down is it, right? How far down would be this distance? How far over would be this distance, right? And then we want to know it's how fast it's going this way, how fast it's going this way, and then make that an angle magnitude vector. That's what we're being asked to do. So basically, if we solve this, it's not so hard. So 5 meters horizontally, that goes here. Right, the 0 goes here, and negative 9.81 goes here always. And then since it's the same problem we're talking about, it's got the same velocity here. So this is, I'm just using this from the previous part of the problem, 7.0908. 7.0908. It doesn't change, right? We don't know the time yet. Let's see. But we'll figure it out from here, right? Our initial velocity here is 0. And I think what happens here is we use S equals ut. In this case, we find the time, right? So the time is going to equal S over u. And this is in the horizontal direction, right? So I'm going to divide this by this. So 5.00 divided by 7.0908. And I'm not using totally unrounded. That's 0.70514. How many sig figs? That's like 5 sig figs. We have 3. That should be good, right? Okay. So basically, the horizontal determines the time now, right? Time goes across. So that is 0.70514. I'm going to store that, just FYI, I'm going to store that in T. All right, and now we can find everything here, right? We can find the displacement, right? I'm going to find the displacement using S as ut. That's 1/2 at squared. Right, now there is no initial velocity, so it equals 1/2 negative 9.81 times our time, right? Our 0.70514. Don't forget to square that. Okay, so here we go. 0.5 times alpha t squared. Whoops. Alpha t squared. I stored it in the letter t, so now I can just use that, right? And I get that the vertical displacement is negative 2.4388 meters. So it ends up down, of course, right? And then let's see, v is, I guess I would use for final velocity vertically, I would use v equals u plus at. Right, so it's 0 plus negative 9.81 times 0.70514. Okay, so negative 9.81 times alpha t, negative 6.917. Right? Okay, so now we want to know what is the position of the ball. Well, it's 5 meters in the x direction, because this is x direction, right? This is y hat, right? Plus negative 2.4 meters, right, in the y direction. Here it is unrounded, there it is rounded, okay? So that's how far over, how far down. If you just write it this way, I'm happy, right? Maybe put little hats on those things, right? Okay, then it says, what is its velocity in components? Well, meters per second in the x direction, right? Plus, and you'd round these to 3 sig figs, just like this. right, in the x direction plus, and then negative 6.92, there it is rounded in the y direction. So far, so good, right? That's our y direction. Now it says draw a picture of it, right? So let's draw a picture of this guy. It's over, and it's down. Now I'm consciously making the down one a lot smaller. It really isn't that much smaller, because I know that this angle has to be adorable, right? Okay. My magnitude is, and this would be, by the way, the speed of the object at this point, right? The magnitude is the square root of 7.0908 squared plus 6.917 squared. Okay. You know the minus sign doesn't matter because it's squared, but actually, surprisingly, it actually does matter on a TI calculator. Okay, so let's go square root of that. Oops, gotta hit enter. Squared. Oh, it's gonna mess me up. Okay, hold on. I gotta delete that. Whoops. Oh. Just wanted to hit delete. That's all I wanted to do here, folks. Okay, and then plus 7.0908 squared. Oh, 9.906. Right, so 9.91 meters per second is this magnitude here. Right, and then to find that angle there is, what is this? This is 6.917, 7.0908. So that's the inverse tan of opposite over adjacent, right? So 6.917 divided by 7.0908. Okay, let's try this. Second tan of 6.917 divided by, now I know this has to be less than 45 degrees, right? 7.0908. 44.289, so 44.3 degrees, right? So here it is in words, right? This works. That's 44.3 degrees, right? There it is in words. There is a picture of it. You need to draw this picture. It needs to show this velocity like this. All cliff problem ones, they'll always be going down. It'll be below the horizontal. When we start doing trajectories that go up and down, you know, the possibility exists for it to be above horizontal or below. But these will always look like this. Yeah. All right.